Okay, now that we have the basics of the components of a solution, let's think about why solutions form in the first place. So by posing that question, what I am asking is, let's say if you have a tumbler and you put some water in it, and you put in a pinch of salt, and you don't actually take the time to stir it, but you just let the salt be. What's going to happen in, let's say, 10 minutes? You would see that the salt would have dissolved on its own, even. Why is that? So, even if you don't provide the energy for the dissolution process, the salt sort of does it on its own. So, sounds like nature has a tendency towards mixing, and why would that be? The answer to that lies in what is called as entropy, which basically means disorderliness. We have an entire chapter dedicated to this, by the way. Whoops. So, entropy means disorderliness. In nature, all processes are moving in a direction such that it leads to a more disordered arrangement. Kind of counterintuitive to what you would say, but this disorder basically means that the energy is more spread. Consider another situation. Let's say you have a container and it has two compartments. You put some gas, let's say you have helium and you have neon in the other. If you don't like those two, you can put any two gases, A, B, whatever you want. You have two gases, and now you're going to remove this barrier. Let's say I remove that. Spontaneously, you would see, without you providing the energy, neon is going to move up in the other direction, helium is going to move in the direction towards neon, and after some time, it'll be one uniform mixture of gases. Why does that happen? That happens again because of increase in entropy. In other words, we can say that any process in nature is going to move in a direction such that the disorderliness or the spreading of the energy increases. So, consider another case. Let's say you have a food color, and you take a glass of water, put in water here, you drop in just one drop from the top. What happens after 10 minutes? Let's say you used blue color. First, it would remain concentrated in this region, and over a period of time, it's going to spread overall. That means the particles of the food color are going to mix with the water molecules, and you would end up seeing a decrease in the intensity of the color, increase in the spread of the energy of the molecules, and hence you're saying that entropy is increasing in this case. Any process which is going to lead to increase in the entropy of the universe, that is a favored process, and you would see that happen on its own. Something referred to as a spontaneous process, but like I said, chapter 18 will deal with this in a really good detail. For now, let's discuss the effect of intermolecular forces on generation of these solutions. We saw in the previous chapter that intermolecular forces do exist between the different particles in solids and liquids, and essentially we have the dispersion forces, the dipole-dipole forces, the hydrogen bonding, and of course the ion dipole forces as well. And these forces may either promote the formation of the solution or prevent it, depending on what the solute is, what the solvent is, and what kind of forces are existing in between those two components of the solution. In other words, we are looking at the solvent-solvent interactions, we are looking at the solvent-solute interactions, and we are also going to look at the solute-solute interactions. Essentially, the intermolecular forces will be existing between each of these three categories. Each of these three categories. And the nature and type of interaction that is existent may either aid to the formation of the solution or may prevent that. So, for instance, if you find that the solute is able to interact with the solvent, you would say, and such interactions are greater than the interactions between solvent particles or between solute particles, you would say that the solution will form. If the solute solvent interaction, so if these are even equal to the solute or solvent interactions, the solution would still form, because then we would still have increase in entropy. So thermodynamically speaking, this will be a favored process. On the other hand, if the solute-solvent interactions are weaker as compared to solvent-solvent interactions or solute-solute interactions, the solution may not form, depending on what kind of disparity you have. Or it might require an elevated temperature, or so a supply of energy in that sense, for the reaction to take place. Now, realize that for dissolution to take place, we have a principle that's called like dissolves like. You may have heard about it, in school, as early as elementary school. Even if you didn't hear about it, you may have actually witnessed it. For example, when you prepare for yourself a beverage, okay, so you pick up your favorite drink and you are mixing some kind of an alcohol with cold water, or milk with water, honey with water, whatever it is that you're making. You have two liquids essentially, and what you see is that such as the case of alcohol and water, you would see that the alcohol mixes with water at all proportions. What does that mean? That basically tells you that probably the interactions between the alcohol and water are kind of similar. And if they're similar, that would allow for the solute-solvent interactions to be stronger than the interactions that are existing between solvent-solvent or solute-solute, so between two alcohol molecules or two water molecules, and that is the reason that the solution will form. Or if you compare that to the example I gave you early on, where we had the case of salt, so we had sodium chloride, and we were putting that in water. And I said that even if you don't shake it, it will eventually dissolve. Why is that? The reason is that water is actually able to break the interactions between sodium and chloride. In other words, it dissociates the salt, and in that sense, it breaks down the lattice of sodium chloride, and the solvent-solute interactions tend to be greater than the solute-solute Coulombic interactions, which is why this solution forms. So a solution will form depending on the kind of interactions that are existent between two solute particles or two solvent particles, and also between the solute and the solvent. So over here, I'm giving you the two examples. We've been discussing this now for some time. If you consider sodium chloride and you put it in water, essentially the ion dipole attractions between sodium and chloride ions and water molecules. So water, like I said, water comes in and it breaks down the sodium chloride into Na plus and Cl minus. The Na plus basically attracts the polar water molecule, and it keeps the oxygen in it towards itself. Cl will do the same thing, and it would pick up it would face the hydrogen end. So that's going to happen. And the ion dipole attractions would be present between the solute and the solvent molecules. Now, if this is a strong interaction between the water molecules and the sodium chloride by itself, then you would say that sodium chloride would not dissolve. On the other hand, if the interactions between sodium chloride and water are higher, are stronger than the sodium chloride system or the water system, then the dissolution is going to take place. Now, if you consider the example of oil and water, in that case, oil basically has a lot of carbon and hydrogen in its structure. And when you have carbon and hydrogens, like a hydrocarbon or a grease type of a base, that automatically renders that particular compound a nonpolar compound. Nonpolar compound. And if it is nonpolar, then the kind of interactions you expect to see would be dispersion forces. And water being polar, since it has that bent shape, water being polar is going to have a dipole-dipole interaction. And specifically in case of water, you will actually see hydrogen bonding. So what we are saying here is you're putting oil, which is nonpolar, in water, which is polar. And since the principle of solubility is like dissolves like, you won't see water and oil to dissolve with each other. And you have seen that. As an example, I mean, if you have an older car, and you might have seen some spots in your garage as your engine oil leaks through, and you're trying to clean that up and scrub that off. And if you just take, like a water hose and try to clean it that way, it's not going to cut it. It's not going to work. Why? Because engine oil has more non-polar interactions. Water, on the other hand, has more polar interactions, so the two don't mix. In other words, what can be done to clean those spots in your garage? You can use a paint thinner, and that paint thinner will dissolve your engine oil, and hence you would be able to clean that particular surface. Likewise, if you consider, having made maybe eggplant parmigiana or something like that, like a lot of cheesy food, a lot of fatty food, and now you want to clean that dish, and you want to think about it that, oh, okay, I'm just gonna rinse it with water, and it's going to be nice and clean. Would it get cleaned? No. You have to always add detergents to be able to clean that. What is the reason for that? Well, the detergent or soap, in that sense, it has a hydrophobic tail. Hydrophobic tail. Hydra means water, phobic is aversion or hatred. So this tail does not like water. What does it like? It likes grease. So this interacts with grease. It has a hydrophilic head. Hydrophilic head in its structure, which means this is a polar end. This is where the charges would be. So this part will interact well with water. So now when you put the soap, or you are actually providing an interface between water and the grease, and hence you would be able to wash off and clean that grease off. So the structure of the soap molecules that provides the cleansing action to cut out that grease from the surface of your dishes. So for example, when you consider vitamins you would know are of two kinds. This is almost like a layman information now. That vitamins could be fat soluble, or it could be water soluble. water soluble. Water soluble vitamins, they will dissolve in your body fluids and they are easily eliminated in the urine, so there is little danger of overconsumption. On the other hand, if you think about fat soluble vitamins, they can actually accumulate in the body's fatty deposits, and so overconsumption of a fat soluble vitamin can be detrimental to health. So you may have to replenish your water soluble vitamins like vitamin B and vitamin C. On the other hand, things like vitamin A, for instance, will be more fat soluble. So I'm going to draw some structures, and you should, looking at the structure, you should predict whether it's going to be fat soluble or whether it's going to be water soluble. I'm just going to draw like two of those, and then we'll take it from there. Let's say these two structures are provided to you and no other information is given as to what kind of vitamin it is. Two labels are provided to you. One is vitamin K, the other is vitamin B5. And another piece of information that is given to you is that vitamin K is a fat soluble molecule. On the other hand, vitamin B5 is a water soluble molecule, and you basically have to put this label by the structure. Now, in this case, the way it's drawn, of course, just realize that each of these positions is a carbon atom, and carbon can form 4 bonds. So if it's forming 3 bonds to other carbons, the remainder is essentially a hydrogen. So when you only have carbon and hydrogen bonds, that basically means that you have like a lot of grease-like structure in this case. And while you do have, so most of this molecule, what we are saying is that most of this molecule, all of this part is very non-polar in nature. So would be this methyl group, so would be this N. The only thing that's polar in this molecule is the C double bond O, but then there is another C double bond O in the opposite direction. So that's going to basically nullify the effect of each other. Overall, this molecule can be considered non-polar. The other structure that I have a C double bond O with an OH. So this is a polar group right here, right over here. You have an amide group. Those of you who are going to go forward with organic chemistry are going to learn about these things in good detail. But the amide group is polar as well. We have an alcohol, so that will allow for hydrogen bonding. So with the carboxylic acid, so with the NH. So hopefully you can see over here there's a lot of potential of hydrogen bonding, and this molecule is polar. So since hydrogen bonding is allowed, this is going to be your water soluble vitamin B, water soluble vitamin B5, and the first one is going to be vitamin K, which is going to be the fat soluble molecule because of the non-polar sense of the structure. Let's now discuss the energetics of solution formation. All chemical reactions basically go through some kind of energy changes, and energy changes will also occur when a solution forms depending on the magnitude of interactions between the solvent and the solute particles. So for example, if you take up sodium hydroxide, NaOH, and you put it in water, so you're generating aqueous NaOH. In that case, heat is evolved, and so the beaker gets hot. Beaker heats up. That means you're talking about an exothermic reaction. On the other hand, if you consider a salt like ammonium nitrate, NH4NO3, and you put that in water, the dissolution of ammonium nitrate is an endothermic process. And it's endothermic because heat is going to be absorbed. The beaker is going to feel a lot cooler. So there are salts, there are compounds which upon dissolution give off heat. On the other hand, there are compounds like ammonium nitrate which absorb heat for the dissolution process, and those are endothermic in nature. There are some like sodium chloride which barely absorb or evolve any heat upon dissolution. And so there are different behaviors that every salt is going to show you. So the question is, why do we see such changes? And the answer to that lies that the dissolution process can be broken down further into three separate processes. The first thing that we have to do is we have to separate out the solute into its constituent particles. Usually this step is always endothermic because you will always require energy to overcome the forces that hold the solute particles together. The next step is to separate out the solvent particles from each other, and this step too will require energy. And the last step is to mix the solute and the solvent particles together. And this step usually should be exothermic because energy will be released as the solute particles will interact through their intermolecular forces with the solvent particles. So we are trying to make interactions, so energy should be released. So let's think about it one more time. What we said is, let's keep the simplest case, sodium chloride in water. So over here I have sodium and I have chloride, and I have sodium and I have chloride, and it's extending as a lattice in this direction, backwards as well, forwards as well, up and down. So it's moving in all directions in a three-dimensional space. You're supposed to break the Na plus and the Cl minus. That's the first thing. So Na plus and Cl minus have to be generated. This step will require energy. The reason why it will require energy is because those are held together by Coulombic forces of interaction. A positive is attracting a negative, and you have to supply the energy to break these free of each other. Likewise, you know that water is held together by hydrogen bonding. And if we want to now place sodium chloride, or at least the Na plus and the Cl minuses, in between the water molecules, so we have to create the space between them so that they mix together, we will have to break these hydrogen bonds as well. And that will require energy as well. So delta H solvent is going to be an endothermic process as well. Endothermic. This is endothermic as well. On the other hand, if we take NaCl and now we place that in between water molecules, so we are mixing molecules now. So you have water, all of this is water, and upon mixing, upon putting the two together, you're going to have the solute in between. So that will be an exothermic process. So one can say that the overall delta H solution overall is going to be a summation of the delta H solute, the delta H solvent, and the delta H solution, or you can call it mix, to differentiate between the two. So the first two are positive numbers. This is a positive value. This is a positive value because those are endothermic processes. On the other hand, the last one is going to be a negative value. And depending on the magnitudes of these individual processes, one can predict whether the overall is going to be a delta H being exothermic, or whether it's going to be an endothermic process. So one can safely say that if the sum of all the endothermic processes, which is the first two over here, if that is about equal in magnitude to the exothermic term, then the delta H solution is going to pan out to be approximately 0, And in such a situation, the increasing entropy upon mixing the two is going to drive the formation of the solution, and the overall energy, even though that remains constant, it's the increase in entropy of the universe, which is why the reaction is going to take place. On the other hand, if the sum of the endothermic terms, if that is lesser than the exothermic term, then the overall is going to be an exothermic reaction, and that will be an allowed process. That will be the factor which will drive the formation of the solution. And if the sum of the endothermic terms is greater than the magnitude of the exothermic term, then it'll be positive. It'll be an endothermic reaction. And if this separation is not too, the difference is not too large, then it will still drive for the formation of the solution. On the other hand, if the difference is too large, then the solution will not form. Let's take a look from the perspective of an example over here. So I'm showing you the sodium chloride in water, and we have been talking about this, that water is able to essentially dissociate the lattice of Na plus and Cl minus. So as water molecules collide with sodium chloride, the ions are going to break free, and more water molecules will then sort of cluster around. So for each Na plus, the oxygen will face the sodium, and there'll be ion dipoles that will get formed. Likewise, you'll have the Cl negative, which is going to face the hydrogen, and there'll be other ion dipoles that will be generated in the solution. And during this process, one can say that the sodium chloride is being solvated until the solution gets formed. So what we are saying is that we have a pure solute, we have a pure solvent, and we have to mix the two together now. So if we have a pure solute, essentially they would be at a higher energy level or energy state as compared to when you mix the two together, again for the concept of entropy that we have discussed previously. So one more time, you need to break the interactions between the solute, you need to break the interactions between the solvent, and you need to make the interactions between the solute and the solvent. In order to break any interactions, just like breaking bonds, that requires energy. So these two are endothermic processes. So delta H, recall from the chapter on thermochemistry from Gen Chem 1, that value will be a positive value. On the other hand, making interactions, just like making bonds, is going to release energy. So your product is going to be an exothermic process. So the delta H is going to be negative. Now, according to the law of thermodynamics, if the total, so delta H solution, as we were discussing previously, it's going to be a summation of these three processes, these three endothermic and exothermic processes. So let's say you require 10 kilojoules for breaking the solute interactions. Let's say you require 5 kilojoules to break the interactions between the pure solvents, and let's say in that process 16 kilojoules was released. So overall you have 15 minus 16, which is going to give you a negative 1 kilojoules value. So this is exothermic in nature. Since it's lesser in energy, essentially the process is going to take place on its own, and you would say that this is a spontaneous process. On the other hand, if the two were exactly the same. So if you had 10 kilojoules required to break the solute interactions, 5 kilojoules required to break the solvent interactions, but 15 kilojoules is given off. So the net is basically 0. What does that tell you? That should tell you that in such a case, you have the formation of the solution, mainly because of the reason that the entropy is increasing as you are mixing the two components with each other. And due to this increase in entropy, the dissolution process will occur. On the other hand, if the difference in energy is too much, so let's say you still give off 15 kilojoules, maybe 15 kilojoules are given off when you mix, but you require, let's say, 1,000 kilojoules to break the lattice and maybe 100 to break the pure solvent interactions. That would basically mean that it's requiring more energy than it's giving off. That means the mixing is not catering to the dissolution process, and then you will not see the formation of the solution in that particular situation. What's coming in the next 4 or 5 slides, I have already actually discussed that, but I'm just going to give it another twist. Any process, again, is considered spontaneous if entropy is increasing and enthalpy is decreasing. So if the delta H is exothermic and the delta S is a positive value, you say that it's a spontaneous process. That doesn't mean that endothermic processes don't occur on their own. For instance, if you consider evaporation of water, even if the temperature is like 10 degrees, so even during cold days, evaporation does take place. And the reason why it takes place is because the entropy is still increasing. You're going from a liquid phase to a gas phase, so the disorderliness in the state is increasing. And these two terms are tied together, what is called as Gibbs free energy, and denoted by delta G, which is the free energy change, according to which delta G is delta H minus T delta S. And the rule of the thumb is that if this delta G is a negative number, then the process will be termed spontaneous. On the other hand, if the delta G is positive, then it will be a non-spontaneous process. So you can envision that for a dissolution process, since we want our salt to be soluble in our solution, if you get a delta G of a negative number, you're going to end up with a negative delta G for when the salt dissolves. When the substance does not dissolve, it will be a positive value. The delta H for this case will be called as delta H solution, and the delta S will be called as delta S solution. And so in that sense, you can perhaps envision, since you're going from a pure solid or a pure liquid to a mixture, you're increasing your disorderliness. And delta H being an exothermic process overall or an endothermic process overall, it's a combined effect. And in that sense, I say that delta S will sort of determine whether or not the overall Gibbs free energy tends to be a negative number or a positive number at a given temperature. So there are 3 things that are going on here, and the interplay of those 3 numbers should give you a negative value for a spontaneous process and a positive value for an overall non-spontaneous process. This is what I was talking about. You have a pure solid over here, you have a pure liquid over here. When you mix the two together to form the solution, you have now increased the randomness. Likewise, if you had 2 liquids, because a solution need not just be a solid and a liquid. You could have a liquid and a liquid system. The word that we use in that case is immiscible, especially if the 2 are soluble at all proportions. but the solution that you end up with is going to have a greater amount of entropy because there is greater mixing and hence greater level of randomness in that system. So again, when something dissolves, there is mixing that's going to take place. And so in general, you will see that the delta S will be a positive number. Delta H solution, like I have talked before, it can be exothermic, it can be endothermic, because it really is an interplay of the forces of interaction between the solute-solute particles, the solvent-solute particles, and the solvent-solvent particles. Those are your three sort of categories, and the interplay between the three is going to give you whether or not you have an overall exothermic reaction or an overall endothermic reaction. So it's kind of difficult to predict what it's going to be if your solute-solute interactions and your solvent-solvent interactions, which require heat, so these are endothermic, and if these are stronger as compared to the solute-solvent, which will give off energy, so the delta H is going to be negative here. It's an exothermic process. That would mean that the overall process requirement, that your overall delta H will be a positive number, will be an endothermic process, and then it will depend on the entropy as to how well it can compensate for this requirement. On the other hand, if your solute-solvent interactions are way better than your solvent-solvent interactions, in that sense you would say that the process overall is an exothermic process, and it will be able to account for the process to go spontaneous at all temperatures. So that's what we want any process to be like. Now, for a lot of common solutions where we are actually referring to aqueous solutions, you can, for example, seawater. You can envision that you have an ionic compound which is dissolved in water. And so for such aqueous solutions, the delta H solvent, which is the amount of energy that will be required to push the solvent-solvent molecules away from each other, and the delta H mix, which will be the amount of energy given off when the solute and the solvent mix together. So these two can be combined together, and they have a specific name which is called as heat of hydration. Heat of hydration. A lot of people would use the term heat of solvation if the solvent was something other than water. But heat of hydration will be the enthalpy change that occurs when a mole of either the solute ions in a gas state are dissolved in water. So because of this ion dipole interaction that exists between the dissolved ion and the surrounding water molecules, since this is much stronger than the hydrogen bonds that are present, the delta H hydration will always have a largely negative term for ionic compounds. So what we are saying here is that if you consider an example such as sodium chloride, so let's say you have NaCl and you put it in water. And I've been saying all along that water molecules come in and they basically dissociate the Na and the Cl, and they give you Na plus and Cl minus. So now you have a situation that you have Na plus, which is surrounded by H2Os, and you have a Cl minus, which is also surrounded by H2O. So these are your ion dipoles. And the amount of energy associated in this particular process is a negative value. It's an exothermic process because it's a solute-solvent interaction that's occurring. In a solvent-solvent interaction, realize that since we are making room between two water molecules, recall from chapter 11, oxygen is directly bonded to hydrogen. That means that this is capable of hydrogen bonding. So hydrogen bonding, even though it's a pretty strong force of interaction, in this case, since you have a pretty strong ion dipole interaction as well, and that is able to cater for the amount of energy required to break those hydrogen bonds. And so one can say very safely that delta H solution, which we earlier defined as delta H solute and delta H solvent, and the delta H mix, these two now have a specific name. These are being called delta H hydration. And if this delta H hydration, if this is a largely negative value, which it would be if you have an ionic compound which was completely soluble in the water, then your overall delta H solution is also expected to be a negative value. So for ionic compounds, the delta H solute is essentially the energy that is required to separate the solute into its constituent particles, which in case of an ionic compound will be the positive and the negative ion. So in that sense, one could say that delta H solute is going to be negative of the lattice energy. Delta H lattice. Recall from General Chemistry 1, whenever ions come together, they emit energy. It is difficult to determine the exact value, so oftentimes you would use Hess law to determine these. But for example, when you have the Na plus and the Cl negative come together, it will give off energy, and essentially the solute's lattice energy, the negative of that is going to give you the amount of energy that will be required to break that lattice. And so the combination of the two, the lattice energy and the hydration energy, is going to give you a sense of whether the delta H solution is going to be a positive number or a negative number. So essentially we're just rewriting the same relationship that we discussed a couple minutes ago, but now in terms of lattice energy and in terms of the hydration energy. And we are about to achieve essentially common ground, so we can set up a rule of when can you predict whether a given salt would be soluble or not. So if you have a situation that the delta H solute is less than the hydration energy, that means the amount of energy required to separate the solute into the constituent ions is less than the energy that is given off when hydrated. So this value is less than delta H, let's write that somewhere, delta H solute. If that number is less than delta H hydration, if that happens, then you can envision that your overall process is going to be an exothermic process, because like we discussed earlier, this was a negative number. If this value is a negative number, this value is a positive number, your overall negative terms are winning right now. So you can envision that this particular process is going to be overall exothermic, and you will see that such a salt upon dissolution is going to get the beaker warmed up. On the other hand, if you had a situation, if you have a delta H solute which happens to be greater than delta H hydration, what will happen in that situation? So now we are saying that the amount of energy required to separate the solute into the constituent ions, the cation and the anion, that is going to be greater than the energy given off. So that would mean that your overall delta H solution should be positive. So this number should be a positive value. It'll be an endothermic situation. And so something like ammonium nitrate, for instance, will be a good example of this, that when it dissolves, it's going to give you a resultant solution which will be cool to touch. And a situation where you have the delta H solute, which is about the same as the delta H hydration. So the amount of energy required to separate the solute into the ions is approximately equal to the hydration. So the delta H is approximately going to be equal to 0. So it's neither appreciably exothermic nor appreciably endothermic. And great examples of these will be sodium chloride, for example, which is not going to go through a noticeable change. So for instance, if you are taking, let's say, making lemonade for yourself, you don't see a big change, a big jump in the temperature of water once you put in sodium chloride into it. So in that case, you're going to say that the delta H solution is going to be pretty close to 0. It'll be about equal to 0 because your heat of solute is approximately equal to the hydration that you're seeing in the system. So again, to reiterate, hydration is the attraction of ions for water molecules. Some people would use the word solvation for when it is a solvent of any kind. So that's a more generic term. Hydration energy or solvation energy will be the energy associated with the attraction between the ions and the water molecules. And the lattice energy will be the amount of energy that is holding the ions together in a lattice, and the interplay between the numbers as to which one is higher is going to ultimately culminate in a positive and a negative value, which can give you a sense of whether the hydration is a stronger process in that particular situation for that particular salt and solvent, or whether it's the lattice which is stronger. So again, for the case of sodium hydroxide, we felt that the beaker was warmer, and that would automatically mean that the hydration is going to be a stronger process in that situation. And the reason again for that is because it's an exothermic process. Heat was given off. Delta H, which is the negative number, is going to be more than the positive number for the lattice energy. All right, let's take a look at this question. The question asks you, arrange the following in order of their expected increasing solubility in water. So you have bromine, you have KBr, and you have C7H8. Notice this particular compound contains only carbon and hydrogen. That would mean that all that you have is London forces of interaction. This is a very non-polar compound. On the other hand, if you consider potassium bromide, you have a positive there, you have a negative here. So there are Coulombic forces of interaction. This is an ionic compound, and ionic compounds are polar compounds. So this is very polar, and it will require a lot of energy to break that, but it will also be very soluble in water. So going by the principle that like dissolves like, KBr should be the one that will have the maximum solubility. C7H8 will be the most nonpolar compound, and that would mean that it would be most insoluble. And Br2, that's going to be the one in between. Now, some of you might think that Br2, bromine, should be nonpolar as well. And in part that's true because you have a bromine, and in the past in Gen Chem 1 we have seen that if you have a hydrogen and a hydrogen, the extent to which one hydrogen pulls the electron density towards itself, the first hydrogen will pull it back, and so the overall effect is that this is a nonpolar molecule. On the other hand, in case of bromine, because of the presence of the d orbitals, because of the size of bromine, we consider bromine to be polarizable. So what that means is that one of the bromine atoms can actually pull the electrons towards itself, the other will be slightly positive, and this is the only reason for this is the size. And you call bromine, iodine, such molecules as polarizable molecules. So anytime there is a source of electron that approaches bromine, that shift in the electron density more towards one of the bromine atoms, that will occur, which is why we call it polarizable, and it is partially soluble in water. So your correct sequence is C7H8 will be least soluble in water, followed by bromine, followed by KBr. And again, in a situation like this, in a question like this, a lot of students, even though they would know the order, they would make a mistake in understanding increasing and decreasing. Increasing means low to high. Decreasing means high to low. And even though it's a common sense thing, a lot of times in an exam situation, we forget about it. So it's a good idea to have a red flag and cross-check and make sure that you understand what the question asks and you are actually answering that. All right, another question here. The question asks you, which would you expect to have larger or more negative hydration energy? Realize that hydration would occur well if the size of your ion is small. It's like saying that if you have like a table tennis ball, okay, and you have a basketball, and you have the same amount of cloth to cover it, which one do you think will cover better? It's an obvious answer that the table tennis ball will be covered completely, the basketball not so much, and that is because of the size of the ion. So smaller is the size, better is the hydration, so that would mean higher will be the hydration energy. So all we're doing here is we are comparing the sizes, because sodium, cesium, lithium, rubidium, these are all ions of group 1. So these are all group 1 metal cations. And lithium is the smallest in size, so that should have the highest energy. The second one is Mg2 plus, Na plus, and lithium plus. There are two things that we are comparing here. One is the size, the other is the charge. So notice lithium and sodium, both of them, they have the same amount of charge. Lithium, however, is smaller. So between the two, lithium is going to have a greater hydration energy. But as the charge increases, the hydration energy or the extent of hydration is going to be better. So one can envision that magnesium, because it has a 2 positive ion, it's going to attract more number of water molecules around it, which means that it's going to go through a better hydration. The size of magnesium and lithium is about the same on the periodic table, something called as diagonal relationship. According to which group 1 and group 2 ions, the size of lithium is going to be similar to magnesium, and the reason for that is if the atomic radius decreases as you go across the period and it increases as you go down in a group, if you go across in the periodic table in a diagonal direction, then it should be about the same. So if size doesn't matter between lithium and magnesium has a greater charge, then of course that should have a better hydration, and its hydration energy should be higher as well.